8.6 Molecular Structure of Acids and Bases. Our outcome is I can explain the relationship between the strength of an acid or base and the structure of the molecule or ion. So we want to be able to compare strength and structure here and be able to do things like predict which acid will be stronger based on its structure. So in order to break a chemical bond, energy needs to be absorbed, and the amount of energy that I need to break that bond is called the bond enthalpy. So this is a measure of bond strength. So bond enthalpy is a measure of the energy that I need to break the bond. It's also the amount of energy that I would release when I form a bond here. So here we have a couple different groups of acids here, and we have their bond enthalpies and their Ka values. So go ahead and pause the video and take a couple of minutes to work on question A. So comparing the acids in group A, how does bond enthalpy impact the strength of the acid? So the higher the bond enthalpy, the stronger that bond is, and the harder it's going to be to break. So that means that the acid is less likely to dissociate and will be weak. So when that bond between the hydrogen and whatever it's bound to is super strong, the acid is going to be weak because it's going to tend not to break apart. So is this consistent in group B and in group C? So we see that within a group, but not group to group, the same trend is going to apply. So let's zoom in on the acids in group C. So looking at the bond enthalpy difference for HBr and HI, the difference between these two is about 68 kilojoules per mole for that bond. So these acids have similar bond enthalpies and they have similar strengths, meaning that they have similar Kas. So looking at HF and HCl. So there's a big difference in the bond enthalpies between these two acids. The HF bond is harder to break than the HCl bond. So one acid is going to be strong, the HCl, while the other acid will be weak. So chemical bonds that have large bond enthalpy values will be difficult to break. How does this relate to the Ka value of the acid? So I'll show you that with an example here. So here's hydrobromic acid. And when we look at this bond between the hydrogen and Br, this bond is pretty easily broken. It has low bond enthalpy. So that means that HBr will dissociate to a large extent, and the acid is going to be strong with a large value for Ka. So we looked at the effect of bond strength. Now we want to look at the effect of polarity. So we've got two molecules here. We have HCl and we have HCCl3. Notice that they have pretty similar bond enthalpies, but their Ka values are widely different. So go ahead and pause the video and work on the questions in this next set and return here when you're ready to check your work. So comparing the bond strength of H to C and H to Cl. Based on bond strength alone, we would predict that the H to C bond should be stronger because it has a lower bond enthalpy here. So whenever we say stronger here, we're saying not the bond, but the Ka value. So it should be a stronger acid based only on bond strength. But then when we look at the Ka values, we see that this H to C bond doesn't give us a strong acid. So compare the difference in electronegativity values now. So based on this, the electronegativity difference between H and Cl is greater. What that means is that that bond is more polar and it is more likely to dissociate in water. So when we have a more polar bond, H2O can interact with the hydrogen and pull it away, causing the acid to dissociate. So we want to look at why the H in HCl is acidic and why the H in CHCl3 is not acidic. So the H to C bond is very weakly polar, and this means that water is going to have a hard time interacting with the hydrogen, and it's not going to be able to pull it off of that acid molecule to dissociate it. So when bond strength is similar, electronegativity difference is going to impact the acid strength. So the greater the electronegativity difference, the more polar the bond will be, and the easier it will be for water to grab one of those H pluses, making the acid stronger. Now, a quick note on electronegativity. Electronegativity is how well a nucleus attracts the electrons that are being shared in a bond. So this depends on a few things. It depends on the number of protons in the nucleus of the atom. More protons means a more positive charge, so that Coulombic attraction is stronger. The distance of the electrons from the nucleus. So electrons that are close to the nucleus will experience a greater attraction than the ones that are far away. It also depends on the amount of shielding between outer electrons and the nucleus. So the inner electrons block the valence electrons from the nucleus, so it weakens that attraction. Now in this example, I gave you some values for electronegativities, but in most cases you will not be given values, and you should infer relative electronegativity based on the periodic table and periodic trends. So a review is found at this link. So in the next section, we want to try to explain which hydrogen is going to be acidic here. So we can have an acid molecule that has more than one H+. So how do we figure out which one is going to actually ionize in solution? So the only acidic hydrogen on both of these molecules is going to be this guy right here. It has a very large partial positive charge, meaning that that bond is going to be very polarized and easy to break. Now, we do have some other hydrogens, but these hydrogens are not going to dissociate off of this acid molecule. So the sum of partial charges on each of the molecules, if we add up all of those values for each of those atoms, we see that the sum for both is 0. And that makes sense because both of these molecules are electronically neutral. So the most acidic hydrogen in each acid is going to be the one that has the highest partial positive charge. So these are the most polar bonds, and they'll be easily broken by interaction with water. So which acid is most likely stronger? So probably our second acid, which contains the chlorine atoms, because the H plus has a larger partial positive charge than what we saw in the acetic acid, our other choice. Now, those Cl atoms are very electronegative, so they pull those electrons away from the hydrogen, which is why it has a more positive partial charge. So now let's look at molecules that have XOH bonds. So for molecules that contain one or more oxygen atoms, the most acidic hydrogen atom is bonded to that oxygen atom. So in group A, why does the partial charge on the acidic hydrogen increase as more chlorine atoms are added? So as we add more Cl minus ions or chlorine atoms, these are very electronegative atoms, and they're going to pull electrons away from the side of the molecule that has that hydrogen atom. So that makes the partial positive larger. Now, the decreasing partial charge on the acidic hydrogen in group B is due to the presence of the halogen that's present in the acid. So as you go down the column for halogens, the halogen becomes less electronegative. So we end up with less electron drawing ability. This makes sense because as we go down, remember that our atoms are getting more and more layers of electrons. So the electronegativity is going to be decreasing. So what's the relationship between acid strength and the partial positive charge on the acidic hydrogen? So the higher the partial positive charge, the stronger the acid, the more ionizable it will be. So in question 14, we're given the Ka of this acid, and we're asked to predict the Ka of this acid. So the main difference between these two acid molecules, this one has 3 chlorine atoms attached to the first carbon, and this one has 3 fluorine atoms attached to that first carbon. So the Ka for CF3COOH should be a little higher than it is for the other acid. This is because fluorine is more electronegative than chlorine. So I would predict that the Ka is probably somewhere around 0.3, so a little bit bigger than what it is for my other acid, based on the presence of the more electronegative fluoride atom. In question 15, we want to compare these pairs of acids and figure out which one has the larger Ka, in other words, which one is stronger. So we're going to consider the electronegativity difference here. So looking at sulfur and selenium. Selenium is going to have more layers of electrons, so its electronegativity will be lower. So the one with the higher electronegativity is going to cause a greater strength of acid because there's more distribution of charge. So looking at the next two acids here, the only difference is nitrogen or phosphorus. So nitrogen only has 2 layers or shells of electrons, whereas phosphorus has 3. So phosphorus is going to be less electronegative. So my stronger acid is going to be the one that has the nitrogen. For my next 2 acids, the difference between these two is that the first one has all hydrogens, and in the second one, 3 of those have been replaced with chlorides. So here's chloride and here's hydrogen. So chlorine is a little more electronegative than fluoride, a little less electronegative than fluoride, and a little more electronegative than hydrogen. So based on this, I would expect this acid to pull electrons towards the chloride side of the molecule, making the partial positive charge on this hydrogen greater. Between H2S and H2Te, so Te is going to have 5 layers of electrons, whereas sulfur only has 3. So that means that sulfur is more electronegative and better at drawing away electron density from the hydrogen atom. And then looking at the last one here, my difference is the presence of 2 oxygens versus just 1 oxygen. So 2 oxygens are going to have a greater electron drawing ability than just 1, making the partial positive charge on the hydrogen greater and making that acid stronger. So for 8.6, here are some reflection questions for you. What factors influence if a proton is acidic? And why are some acids stronger than others? Explain using an example from this topic.